So I'm just going to quickly redraw my two configurations. So this is the reference. This is the current. Okay. Now you notice I tried to use the word configuration and not frame, not reference frame, not current frame, because there's really only one frame, right? In this class, we're primarily just going to deal with a Cartesian inertial frame, okay? That doesn't mean that we couldn't also develop all this, and if you ever take a sort of dedicated class in continuum mechanics, you will do it. You'll develop all these same equations in polar coordinates or arbitrary bases. But for the most part, we're talking about one reference frame that, you know, has the components x1, y, x2, x3. And, you know, I'll try to use x1, x2, x3. It's possible I might use x, y, z. So from this frame, we can draw a vector to a point. So let's mark a point x, okay, and draw a vector to it. And that point x is really, it's a vector. I mean, it's, let me move it a little bit just so you can see very clearly. It's a vector x. So it has components x1, x2, x3. And that after some deformation occurs, that same point is now going to be at this point, little x, right? It's also a vector. So the distance between these 2 points, or the vector between them, is something we call the displacement. So it's a function of big X and t. It's a function of big X because it started there, and time, right? So this is, I'm just drawing vectors, right? So let's take another point, Q, and track its motion over time to little q. Now you'll notice that a common thing here. In the reference configuration, coordinates that are tied to the reference configuration, I'll always use capital letters for. Coordinates that are tied or in the current or deformed configuration, I'll always use lowercase letters for. And I'll try to be very judicious about putting little arrows over my vectors. Okay? So if you catch me not doing that, please correct me, because it's important. And so, you know, Q and little q, big Q and little q are also vectors. By the way, I mean, I know on this course schedule it says the class is from 10 to 11. Does anybody know, does it actually the bell ring at 11 or does it ring at, I'm sorry, at 11 to 12. Does the bell ring at 12 or does it ring at, it's going to ring at 11:50. So we have like 5 minutes? Okay. Sorry, I never actually taught a Monday, Wednesday, Friday class. Maybe I did years ago, but it's been a while. All right. So the displacement between the two q's is also, you know, u, and this one is a function of q and t, right, where t is time. So we're just writing vectors, so through vector addition, it should be clear that I can write little x and little q through vector addition from big X and u, right? So just vector addition, right? I have little x is equal to big X plus u big X in time. And little q is equal to q plus u q in time. Right. And so clearly both x and q are functions themselves of x and time. And q and time, right? Because, I mean, clearly they're functions, right? I can write this in terms of big X. Clearly it's a function. I think probably in the 3 minutes left, it'll be useful to just be very explicit about something. When I write big X, right, it has the components x1, and maybe from undergraduate vectors, you would call that I hat, right, in direction, plus x2 j hat plus x3 k hat, right? Maybe you did that as an undergraduate. But here we're going to use something a little more general, in that we're going to say that x1 is equal to e1 hat, and I'll use a hat there, just like plus e2 hat plus x3 e3 hat. So you can sort of think of e1, e2, e3 as I, j, and k, okay, for this class, because we're going to be sort of doing everything in the Cartesian frame. But by writing it this way, it allows us to do more general things later. In other words, all the concepts will apply when those basis functions are functions themselves. Right? So if the basis function is a function of something, which would be the case in like polar coordinates or spherical coordinates, then we can still develop all the right equations. We just have to be very careful about keeping track of our basis functions. But for the purposes of what we're going to do in this class, you know, e1, e2 equals e1, e2, e3 is I, j, and k. They're unit vectors in the Cartesian directions. Okay. But another thing it allows us to do is to introduce a notation that is a little bit more compact, and that is that a vector x is the summation from I equals 1 to 3 of xi ei, right? That clearly is just another way to write that equation, right? Clearly. But what I'm going to do next may be new to you, especially the undergraduates. I'm going to introduce a notation called indicial notation or Einstein notation, because he introduced it, where anytime I have a repeated indice, so anytime that you have any term, and what I mean by term, it could be any multiplication of things, right, separated by a plus or minus sign. Anytime you have any kind of multiplicative term that's together like that, when you have a repeated indice, it implies summation. So this equation and this equation are exactly the same. I just dropped the summation, because later we're going to have these things everywhere, and we're always summing over 1 to 3, right? And there's 3 Cartesian directions. So we're always summing over 1 to 3, so let's just get rid of that extra term, right? So we can make our equations a little more compact, okay? And later we'll do some manipulations, and this notation allows us to you know, do some things in a little bit nicer way, okay? So this is called indicial notation or Einstein notation. And it just, whenever you have a repeated indice, it implies summation. And there's a couple of other rules and tricks you'll learn along the way. Most notably, any time that you do have a term that has a repeated indice, the repeated indice can only be repeated once. So in other words, I could have something that's like AI, BI. That, in fact, is just the dot product of two vectors A and B, okay? The components of two vectors A and B. But what I can't have is CI. That doesn't make sense, right? Because in isolation, this is a sum, and I've summed it up. That's a scalar, right? So then I can't sum over I again, right? So if I really wanted to multiply all three while summing, I need to put the explicit summation sign out there, okay? So you can't have more than one repeated indice in a term. You could, however, have something like this. So you have a repeated over the I and then a different indice j. That's called a free indice. And in this case, you'd end up with a vector that has the number of components of j. And we'll learn more about how to use these things sort of along the way. A lot of times people will teach the indicial notation in isolation, so it's like a preliminary part of the class. I kind of just teach it on the fly. I think it's more useful to just see it in practice and get some see how it's actually used than to just give you a lot of problems with arbitrary vectors A and B and tensors Ij and things like that, and just have you do a bunch of manipulations for no reason. All right. So we're going to stop here. I'm going to actually start with this picture next time because we didn't really finish the kinematics that we wanted to talk about here, but we'll pick up from here next time.